Hello, welcome to the technical engineering video for Movie Phase 3. If you haven't already, check out our introductory video to learn more of who we are and what Movie is. In this video, we'll go into greater detail about the specifics of the design of Movie Phase 3. We joined this project with the lens assembly and the door and mirror assemblies already designed, as well as the camera elements, including the Photech image intensifier and the camera detector already specified. Our first task was to design a way to integrate and align these assemblies and components. The lens assembly was designed to mount exclusively from the bottom, whereas the door assembly was designed to mount from the sides, and the Photech tube had its position relative to the lens specified, but had yet to be designed a way to mount it. Proper alignment is mission critical because the incoming light must be accurately focused on the camera detector. To ensure for proper alignment, we decided that all assemblies should mount primarily to the same surface on the bottom, and to use intentionally loose tolerances to allow for adjustments to be made during the assembly and alignment processes. The previous team that designed the top door designed it to mount from the sides, but to work with our frame design, some post-manufacturing adjustments had to be made to allow for the door to be mounted from the bottom. The door assembly is now held in alignment with bolts coming in from the bottom, as well as supported by pins that are inserted on the sides after alignment. To mount the Photech tube, we designed a mounting apparatus with flexure blade interface. The tube cannot carry loading, so a mount was needed to be designed to absorb any vibrational loads. In the final design, aluminum towers connected to an aluminum base at the bottom support 3 titanium flexure blades. The tube attaches to the blades at their respective centers via aluminum standoffs. 6061 aluminum was chosen for most features because of its high specific strength and its ease of machining. To absorb any vibrational loads and to prevent them from reaching the Photech, titanium was chosen as the flexure blade material because it has a higher elastic modulus and much higher yield strength, meaning it can withstand much higher loading than aluminum without plastically deforming. Importantly, the flexure mount is designed to allow for adjustment of the tube position during assembly in all 3 primary axes. This will ensure that the tube can properly be positioned in relation to the lens to capture incoming light.
Ultimately, the datum plate is the feature we designed to facilitate integration and alignment of the assemblies. Intuitively, tolerances on the datum plate should be high for optical alignment. However, to save on machining costs, we decided to shim components during assembly. Our next task was to design an accommodating structure. There are many features of the structure that are important to point out. The first feature is the opening on the front. One of the primary requirements for the structure was to allow the spring-loaded doors to open. Once opened, the structure needs to stop the doors and hold them in position, giving reason for the next noteworthy features. These Delrin stops absorb the impact of the doors, and the top stop holds the top door in place such that the top mirror is properly lined. The next feature is the hole in the top plate. Before and during launch, the inside of the satellite must be maintained at a positive pressure and continuously purged with nitrogen. So a purge port for insertion of a hose has been included at the top of the structure. Another feature is the open backplate. Movie is currently a 2U satellite, but a third unit will be required in the future for telemetry. For that reason, the backplate was designed to provide structural support, but also allow for access for the future third module in the unit. The side plates also have a noteworthy design. The mass of the satellite must stay under 2.66 kilograms. To ensure that Movie is within mass tolerance and to help properly position the center of mass, the plates were designed with cutouts that take away mass but do not compromise the structural integrity of the satellite. For ease of assembly, the side plates were split. There are a total of 4 side plates, 2 front plates, shown in green, and 2 rear plates, shown in purple. The final important feature to point out is the door seals. To prevent contamination of the optical equipment by foreign object debris, the entire structure needed to be sealed. Viton seals, highlighted in red in the image above along door edges, provide this function. One challenge to sealing the structure was the need for the doors to swing open. Friction opposing the motion of the doors at the hinges could compromise their ability to open. Rather than using Viton, Delrin was used to seal hinges with its lower coefficient of friction.
Our final task was to test the integrated structure and critical assemblies for vibrational stability. Unfortunately, due to COVID-19 restrictions, we were unable to do any testing. To facilitate testing in the future, however, we designed and manufactured the on-ground orbital deployer simulator. This structure imitates the boundary conditions Movie will experience when inside the P-pod during launch, and will thus be an integral part in the design verification of Movie. Though we were unable to test our design in person, our confidence in the design is elevated by the analysis we ran. For example, we used FEA to determine an appropriate material and thickness for the flexure blades. In one study, we compared the thickness needed to sustain a 100G load without plastically deforming for both aluminum and titanium alloys. Through our analysis, we determined that aluminum blades would need to be unacceptably thick to sustain such high loads, while titanium could sustain loads and maintain dimensions that would allow it to deform significantly and thus absorb vibrational loads before they could reach the photek. 100G load cases were used in initial design as a conservative approximation before performing more detailed vibration analysis. We ran a similar study for the instrumentation frame panels. Roller boundary conditions were placed along rails and 100G static loads were applied to the 6 principal axis directions. These were remote loads used to represent forces on the frame plates by instrumentation structures. Max displacements were under 75 micrometers, and a yield factor of safety of 2.25 was obtained. Results were validated with a convergence study. This concludes our technical presentation. There is still significant work left before Movie is ready for launch, but with the help of our advisors and sponsors, Movie Phase 3 is now complete.